Good afternoon. It's September 29th, 2025. Telecommunications, TELE 1022, Venture College, London, Ontario. All right. So I'm going to go a couple of slides back from last time, just so we land on the proper railroad. I don't know if my comparisons are okay this week here. Anyways, just so we get on the road with the show on the road properly. All right. Okay. So we were talking about the transmission lines, and I gave you a bunch of different examples on characteristic impedance and all the other stuff. So please refer to the previous video if you haven't seen the lecture live. All right. Now we have 15 people out of 22, I believe. So that's pretty good turnout. So okay, let's continue with this thing here. We got some loads to go through. All right. So here. All right. So just as a review from last time, the transmission line theory, transmission lines, functions and characteristics. We take a look at various types of transmission lines. We will define these lines as conductive connections. Well, these are the links, part of the whole transmission model. In many cases, the same type of lines will carry the power, and in some applications, they carry both electrical power and the signal power. We talked about that last time. The best example of that would be the PoE, which stands for Power over Ethernet, and this is to provide the power and signal on one Ethernet cable to whatever the device. It could be wireless access point in the ceiling, or it could be a VoIP telephone, or what else could it be? These are the two examples that are the most common this time. Oh, security cameras as well. Okay. Okay, all types of transmission lines have losses, and we'll talk about some of those losses and some of the mishaps that are happening within the lines. We do need to consider those, and we talked about those a little bit last time already. Although we will be looking at the conductive connections with copper, and again, last time we talked about what we consider as copper, which is the metal type of metallic conductors. It could be aluminum, it could be gold, could be silver, but as a classification for the simplicity of things, we call it copper. And the other two would be fiber, which would be fiber optics, and air, which would be electromagnetic waves distributed over the, well, airwaves. Okay. So the links, for the most part, we consider copper, fiber, and air. That's how we call those things. Okay, although we are seeing wireless transmission finding its way into many applications, there are still many applications for transmission lines. And we also talked about that as a review. Quite often, wireless is not welcome in certain networks, especially with some of the highly secured networks. For example, banks, or maybe some government institutions, office areas. For the security purposes, some of the offices do not want any kind of wireless communications between their computers and their server. Is it possible to replace all wired systems with the wireless solutions? So that's kind of like a half tricky question. Let's say even if security was not the issue, sometimes the number of devices in one area is so huge that sometimes we could run out of bandwidth when it comes to the wireless solutions. So wire is getting strong. Well, is getting strong. Wire holds strong. Wire as type of copper or fiber. Okay. Um, All right, transmission line types. We talked about the coaxial cable, twisted pair, two line lines, and what is that? The conductive. Well, mm, yeah, you will have some of those as well. Those narrow conductive trays. I've seen some of those data cables that you can stick behind the baseboard. Not a fan of those, right? However, they do exist. And well, telegraph lines. Although we don't use telegraph anymore, but the idea of utility poles is still there. Quite often you're going to see those utility poles all over the place if the communications lines are not run underground. You also have utility poles on which, for the most part, right now you can see a lot of fiber optics being suspended. All right. Okay, two-wire ribbon cable. One of the most basic cables is a twin lead with two conductors embedded in low loss dielectric. Dielectric is the another name for insulator. So they're insulated. There is also an open line version as well with exposed conductors. So there's no PVC or any kind of artificial man-made thing holding it. So there'll be just two lines separated on maybe on some standoff insulators, and they'll be suspended. Neither was very popular. Neither one of those, either the dielectric one and the separated by air, but they were cheap. So better than nothing. Sometimes something is better than nothing. Sometimes nothing is better than anything. But in this case, something would be better than nothing. Applications include television antennas, leads. Yeah, these were very popular lines to connect the antenna on the roof with your television set. That was during those times when some of the TV stations were broadcasting their channels over the air. Multicolor, multi-conductor ribbon cables are still quite popular for the lower frequency digital applications. Multicolor conductor ribbon cables, okay, as opposed to the Ethernet kind of a concentric like, because data cable is not a concentric, but it looks kind of round, right? All right. Twisted pair consists of two insulated wires, and the category number defines, and we talked about that last time as well. What is the purpose of the twist? Believe it or not, it was the idea was who came up with the idea was Mr. Alexander Graham Bell. So the idea is quite lengthy in time. Um, well, one thing I forgot to fire up was my board. Let me just get this thing up so we can kind of repeat of what's going on with the twisted pair. Why do we have twisted pair? Or I could do something else as well. But since we are doing that, I'm just going to fire up my board. Correct. Oh, yeah, I was playing with some of the humorous stuff to give you some marks. I never carried through with that idea. Anyways, yeah. All right, so I got my board, but I think I also have that in one of my presentations. Let me just get this thing right here. There you go. Here's a twisted pair. We talked about that last time, but here's the idea of a twisted pair. Let's say we have unshielded twisted pair, and we have shielded twisted pair. UTP, STP. What is the idea of twisted pair. Let's say this is a conductor, and now let me just fire up my show here. So let's say this is a conductor that is connected somewhere, and it's connected somewhere on the other end as well. And let's say there is a current flowing through this conductor. What is this current going to do? It is going to, well, because of the current flowing, we're going to have electric field and we're going to have a magnetic field. Electric field points with the direction of the arrow, and the magnetic field is perpendicular, circularly perpendicular to the electric field. So altogether we have electromagnetic field. All right. Now, which way does the magnetic field spin? Well, if you have a corkscrew that you use for opening your wine bottles, the direction, considering the conventional current flow, the direction of the current will be the corkscrew going into the cork, and the spinning righty-tighty will give you the direction of the magnetic field spinning. All right. Now, let's say within the proximity of that conductor, we're going to place another conductor that is not connected to any power supply. Let's say it could be just a dry conductor, not connected anywhere, or it could be just connected to some sort of a resistor and no power supply at all. If that wire finds itself within close proximity of the wire that already conducts current, then the magnetic field is going to have enough induction influence over the other conductor that is going to induce the current flow in the other conductor. So we call that thing induction. Yeah? So well, that's the phenomenon that we're dealing with. Okay, and the current is going to flow through that. Now, there's things are a little bit more complex, because in order to induce the currents, the magnetic field has to be changing and all that stuff. So this thing works better with the AC rather than DC. That's why the transformers that we use, transformers work on DC currents only. Transformers do not work on DC. All right, so crosstalk in electronics, crosstalk is any phenomenon by which a signal is transmitted. By the way, you have that presentation already uploaded. It's a supplementary presentation. So crosstalk is any phenomenon by which a signal transmitted on one circuit or channel of a transmission system creates an undesired effect in other circuit or channel. So if we're talking about using transformers, power transformers, or even audio transformers, then we want that thing to happen. But if we are if we're talking about two transmission lines close to each other, and sometimes the transmission lines will be like a lot of them, and they will be in very close proximity with each other. Like, for example, a bunch of data cables. Well, the bunch can consist of 100, 200, maybe 600 wires altogether. So there's going to be a lot of things going on, and we don't want crosstalk. We do not want the signal crossing from one circuit to another. Crosstalk is usually caused by undesired capacitive and inductive or conductive coupling from one circuit or channel to another. In structured cabling, electromagnetic interference from one pair to another. We don't want that. In analog, let's say we have a couple of wonderful people having an extremely pleasant conversation on one line, and then there's another conversation happening on another line, and if you see that those two lines run close to each other, and if they are straight lines, which means the pairs are not twisted, the possibility of a crosstalk is high. Almost 100% that's going to happen. Yeah. So that's why Mr. Alexander Graham Bell noticed that long time ago and decided to come up with a twisted pair. All right. Like so. If you notice, a twisted pair idea is, well, this Ethernet cable, and this is Cat6. How can you tell it's Cat6? It's because it has that separator. You see that separator right here? It's a plastic channeling, physical channel that houses each pair. So in this cable, each pair is twisted, and each pair is twisted at a different rate. Why do we twist those? It's because we don't want that electron or the magnetic field that's spinning around every conductor. We don't want that to have enough consistency, so it can affect another circuit. So this electromagnetic field, because of the twist, is kind of directed all over the place. And then look, if you have another pair beside it, which is also twisted, it's very hard for those pairs to align, well, in order for a signal to jump from one pair to another. But then look, those pairs are actually twisted at a different rate. So that's even less possibility for the signal to get enough wind to cross from one pair to another, because the magnetic field is not going to be consistent or uniform enough along the length of these two pairs or the other two pairs. You see, every pair has a different rate of twist. And then if that wasn't enough, there's a separator inside that not only the pairs are twisted around themselves, they are twisted around each other as well with that separator here. Yeah? So that's the idea of a twisted pair. So for the purpose of the crosstalk, or to eliminate crosstalk, okay, twisted pair cables consist of insulated wires. The category number defines the design performance, and we already talked about that last time. Cat3 is typically not used anymore. Cat3, if you hear Cat3, that was mostly used for telephony, and it was enough. The specifications were enough for the voice. Now, when the fax lines came, those Cat3 twists were beginning to be, well, pushed to their limits. So Cat5 was introduced pretty quickly, and then Cat5e stands for Cat5 Enhanced. Then was introduced, and then slowly right now Cat5e is being kind of faded out on the account of Cat6, which seems to be the lowest category cable right now that you can buy off the shelf from any distributor that carries those cables. Okay, so it's Cat3, Cat5, Cat5e, Cat6, Cat6a. The A stands for amended, which means basically enhanced. There's also Cat6e, which is somewhere between Cat6 and Cat6. It's almost Cat6a specifications. And if you want to look at those specs, we have them in that one right there. What do we have here? All right, see, here's the transfer speed and bandwidth. Transfer speed has to do with the digital signals, digital pulses being transmitted, how quickly or how fast can we transmit them, and the signal still being understood on the other end. And the bandwidth is the analog signal, what kind of frequency you can run through that cable, so the frequency can be carried and understood at the other end without any aliasing. And aliasing is it's a frequency type of distortion or resolution related distortion. So you can see here now. Also, I mentioned last time that look, see Cat5, Cat3 is not even mentioned here. Cat5 has a transfer speed of 100 megabits per second and bandwidth of 100 megahertz. Cat5e, so we can go to 1 gigabit per second. And as we remember from last time, we measure the speed in bits per second, not bytes per second, bits per second. Storage is measured in bytes. And of course, there is no such thing as per second, because storage is not time-related thing. Okay, so hard drive has 1 terabyte or 500 gigabytes, but a cable can carry signal, digital signal, with the speed of 1 gigabit per second. Okay, Cat 6, you can see also length related. Most of the Cat 5e, not too long ago, I would say all Cat 5e cannot be any longer than 300 feet. And to end, it's actually 328 feet. However, we don't want to run cables longer than 300 feet because we still have to account for the cords or patch cables to be connected to them. And they also do have length. Okay. So you can see that, for example, Cat 6 has two different specs here. It can transmit 1 gigabit per second, or it can go to 10 gigabits per second, but only uh, um, up to 180 feet. Will the evaluations cover the cable specifications? I'm not going to. Well, depending on what format the test is going to be. If I give you the test in class, I'm going to adjust those questions so you could apply logic over trying to remember the exact specifications. I'm in this business for 30 years, more than 30 years, and sometimes I have to look at tables. So why would I expect you to remember all that? But if it's an open book test, then I might ask you that. So you just have to know where to look for things. So um, where were we? Yeah, okay. So Cat 6 can go to 10 gigabits, but only up to 180 feet end to end. Right? If you want to get 10 gigabits full length or 300 feet, then you need to go to Cat 6A, and it's a heavier cable, way more expensive. The jacks are more expensive. It takes longer to install. It's way more expensive installation, and so on. At some point, you might want to just decide to go with fiber. Right now, when it comes to the copper cabling, there's another cable that has been introduced to the market. And where do I have that? Um, um, I have it somewhere. There it is. There's something that's called a game changer cable. And if I'm just going to try to zoom in a little bit. The game changer cable. It's an Ethernet cable. It is a game changer, and the name of the cable actually is a game changer. All right. It can give you 1 gigabit per second and 1,000 watts, sorry, 100 watts of a PoE, which is power over Ethernet. Um, uh, what was it? 1 gigabit per second over 656 feet, while all the other cables were up to 300 feet only. Now you can have 1 gigabit per second, which is, if you look at it, uh, 1 gigabit per second over 656 feet, which is 200 meters. Or I can give you 10 megabits per second up to 850 feet. So 1 gigabit, that's Cat 5e. Not very often you might want to use that, because if you have greater lengths, then you might want to use fiber. However, in some cases where you have no choice, you might apply that game changer cable. I just want you to know that this thing exists. All right. There we are. Good. All right. So that's the idea behind the twisted pair. Demands on the category X, which would be category whichever, Cat 5, 6, 7, or whatever. The need for higher data rates continues and is driving the need for higher performance of the cables. Cat 8 is expected to handle what 40 gigabits per second. One of the advantages of this design is that these cables can use low cost RJ45 style connector. What does RJ45 look like? RJ45 looks like this. It's just an Ethernet cable. RJ45 modular plug. And well, what is that RJ coming from? RJ comes from registered jack. Okay, and registered jack, just some of the jacks, some of the equipment had to be regulated. It goes back to way back when the telephones were just becoming somewhat popular and then more popular. Just so everybody and their brother who are doing installations, the whole industry had to be standardized so it doesn't get out of hand. Right, so then RJ stands for registered jack, and the 45 means nothing except it's just a cataloging number. So we have RJ45, RJ21s, which would be the end-funnel connectors. They look like a like a sideways pipe, and other RJ12, 11s, and so on. So where are we here? RJ side connector. So those installations are quite cost effective, I would say. Now, depending on what type of installation, because if you have Cat 5e type of installation, it's not going to be as expensive as Cat 6. Now, Cat 6a is going to be way more than Cat 6 installation, and so on. It goes with the time of doing of the installation, because time is money, and it actually adds up. And then the cables are more expensive, different prices, and different types of jacks are also more expensive. So just a regular Cat 5e jacks might cost pennies, and Cat 6a connectors could cost well, $20 per connector. Yeah. Or fiber optics as well, $20, $25 per connector. All right, so higher data rates, critical performance requirements are attenuation and crosstalk. So these are our enemies of the telecommunications: attenuation, which means degrading the signal over as it travels through a link, and the crosstalk, which we just talked about. Attenuation is the measure of signal loss traveling down the wire, and the crosstalk is a measure of coupling between wire pairs. This is sometimes heard on analog telephone lines. So when I was showing those two conversations of the two people, if the wire was those two wires were in close proximity, a crosstalk could happen, and it was quite popular in well, way back when, up to about late 90s and early 2000s. Then I don't think I have heard crosstalk on the phone line for a long, long time. Although you would hear crosstalk and it would manifest itself as you're talking with someone on the phone, and all of a sudden you can hear someone cutting in. Is someone participants? Someone trying to get into our. Let me just see here. Who is that? Invite people. Oh no, it's just an option. I thought someone was trying to get in. I couldn't get into the presentation. All right. Crosstalk would be it would be an analog type of conversation because we talk analog. We don't communicate with each other through our voice in a digital sort of way. That would be funny. But in that case, the interference in an analog form, it would be annoying. Sometimes a nuisance, sometimes more nuisance than other times, but you could still carry on with the conversation. Now, when it comes to digital, things are different. If there's a crosstalk in digital transmission line, the transmission completely goes dead. Okay, it's just the transmission cease to exist. Simply because the ones and zeros that are being transmitted from one end to another, they are time aligned. And if you introduce other ones and zeros spikes, while on the receiving end, the receiver is time aligned and it's time sensitive, it has to it's listening to certain amount per second, certain amount of pulses per second. It's called baud rate. And if you introduce some other confusing pulses, then the system will not know what to do with that information, those extra zeros, and it's just going to shut down the transmission. So the difference between interference with, as a summary, between the analog and digital transmissions is that in analog, it could be annoying, or in some extreme cases, the interfering station might take over the whole transmission if the signal is strong enough. But for the most part, it's annoying. In case of digital transmission, a crosstalk will shut down the transmission completely. All right. Another important measurement is a return loss, which is a measure of the ratio between power transmitted and power reflected. Keep that in the back of your mind because we'll talk about that later, a couple slides down the road here. So return loss. Basically, the signal can bounce off if the line is not terminated properly. Some of the signal might bounce off that connection and start coming back. It's not a very happy situation. Right, coaxial cables. Coaxial cables fit into two categories: air coaxial cable or solid coaxial. Solid coaxial is more popular and both functions the same way. The solid coaxial has slightly higher losses than the air. Well, this would be the solid coaxial cable right here. It's got a center core and it's got outside braiding and it's separated by dielectric, but it's a solid piece of something. Right? It's a dielectric, it's an insulator. The air cables they would look like, here is, see if my drawing skills are going to be. Let's say there is a big antenna mast. Yeah, that's a big antenna mast with a huge type of a transmitting antenna, whatever. I'm just doing surreal things. And from that little house, the transmission house, there will be a coaxial cable, and I'm going to magnify that. It is going to be something like this. All right, and over here it's going to have the center core, which is going to be inside that, and between that center core and the outside conductor, there is just air. And how that is being accomplished is that once in a while, there are going to be some standoff insulators inserted into that line. So the most thing that separates them is air. Okay. But these are thick cables. How thick? Very thick. Thickness of your arm. Okay, so there are with all different specifications for loss, fire safety, impedance, frequency, weight. Weight is one of the things why some of those big cables are just air separated. Peak power, how much they can carry power during the peak performance, and voltage standing wave ratio, which is also one of our enemies. We'll talk about those too. An aluminum exterior braid is often used to reduce cost. So there will be a copper here and aluminum braid. And also aluminum is lighter, or aluminium. Balanced and unbalanced lines. Do we talk about that? I've given this lecture so many times that I can't remember. Balanced and unbalanced lines. All right. quite often used in audio type of signals, however, not only. Yeah. So here's a Shure SM58. That's a performance that I was doing some nights for a few years ago. So I don't have to give a reference to the picture because the photo is mine. All right. Now here's something that's called quarter-inch plug. Now look, this one has tip and ring, and this one has tip, ring, and sleeve. What gives? What's the issue here? Okay, so this one can carry balanced signal. This one can carry unbalanced signal. What's the idea? It's also XLR, which is a typical microphone type of a cable. Here's a female version. Here's the male version of the plug. And here's a pinout. One is the hot, one is the cold, which is the inverse of the hot. And of course, you have a ground reference going all the way through. Now, the difference between balanced and unbalanced signal. On top here, we have unbalanced signal being carried through. And over here, we have something that's called a balanced signal. All right, so unbalanced signal, we have a signal going through a line, and if noise affects that, there could be a spike from electric motor. It could be some car driving by, some of the old cars. It could be a lightning storm somewhere, and it's going to impose itself onto a signal, and it's going to be carried. The noise will be carried through with the signal, and through the amplifier, the signal is going to be, it will be amplified, and the noise will also be amplified. So unbalanced signal will carry signal as well as noise. If you have a strong signal, like from a keyboard, which would be keyboard would carry, it's an active device which can um, um, just looking at the, no, these are some old chat here. If the signal is strong enough and the signal to noise ratio is good, so then the signal is going to be really, really small, and you might hear some hiss, but it's not enough. So the signal can be considered as clear enough. Right? Now, if you have weak signal from weaker instruments, like for example, a microphone has 1 millivolt peak to peak as opposed to 1 volt peak to peak, then the signal is comparable to the noise. If you had that happening, you would hear a lot of noise with the signal. So we use something that's called differential amplifiers, and I showed you that already before. The noise, okay, the differential amplifier detects the difference between those two lines here. So the balanced line has three cables or three conductors, not cables. One to carry the signal, the other to carry the mirror image of the signal, and here's the virtual ground. Remember, op-amp is awesome for the differential amplifiers. So when the signal is inversed, it's being treated as a signal and it's being passed through further. And if noise is in phase, it is going to be ignored. So you can carry weak signals over longer distances involving the balanced line. And here is the example of an unbalanced type of a plug or jack. So here's a tip and ring. That's called tip. That's called a ring. And quite often guitar, active guitar, keyboard, or line patch. If you want to do some patch chords. Noise present on the output. So you want a strong signal. So it's less comparable to the noise hisses that are just present. You can't escape that. Now, with the balanced signal, you can use either the quarter inch, and it's quarter inch because the diameter of this plug is quarter inch. So you can have this type of a plug, quarter inch, or you can have XLR. Both carry the same type of signal. Here's tip, ring, and sleeve, and here is XLR pin 1, 2, and 3. Here's another visual. Here's a source signal with the noise, is getting with the noise through the amplifier, and then output device of whatever it is carried through the balanced signal. The noise is in phase because if those two conductors are going to be in close proximity to something that produces noise, it's going to produce the noise in phase in both conductors, which is going to be ignored, and only the mirror image of the signal is going to be carried through, and you're going to have a beautiful, clean signal. You can pause if you want, if you're watching the video, and you can build this thing yourself on multisim. So here is the simulation of a mirror image of a signal, and on the oscilloscope right here, you have the signal going, mirror image of it, and that amplified signal, nice and clean without the noise. With the noise, I introduced a couple more generators, but these are the noise generators. So these two are out of phase, and these two is going to be in phase. And as a result of which, here, you have a noisy signal, but the signal is out of phase, which we want. It's a mirror image of those two lines. And then the noise, see here, the noise is in phase, and it's ignored in the through the differential amplifier, and you have nice, beautiful, clean signal on the output of the amplifier. Okay. All right. Okay, now how can we convert an unbalanced signal to a balanced signal? Most transmission lines fit into two categories: balanced or unbalanced. Okay, the center conductor in a coaxial cable carries the signal reference to the other ground conductor, and this is an unbalanced line, all right? Because we just have two conductors, that's it. In two-wire conductor line, the current flows in two-wire conductor line, two-wire line, two conductor line, okay. The current flows in each line, but which we talked about, 180 degrees out of phase. Any unwanted noise is canceled. This is called common mode rejection, and which can be 40 to 70 dBs. That's like a lot. Okay. And it is very good. Yeah, I just said that in a different way. We can convert from balanced to unbalanced signal using signals called balloon or balloon, depending where you are. It's a simple transformer idea. Here's an unbalanced signal, and you just grab a center tap, connect that to ground, you affect the whole thing. So in these, if you connect the center tap to the ground, then you're going to have a mirror image of the signal through each of those wires, and you can have that ground carried through, connected, or you could have, it even works if you lift the ground on the receiving end here. So that can also work as the simple conversion from unbalanced signal, transmit that signal over longer distance so the noise doesn't affect that. And over here you have another balanced, unbalanced signal, because maybe that's what you want. Characteristic impedance, we talked about that. What that is, it's an infinite. Okay. Again, as a review, when it comes to coaxial cables, the amplifier transmits waves. The waves carry through, they travel. They enter the pipeline of a coaxial cable. The wave is inserted and it travels along all by itself. Once the wave is pushed into the wire, the wave travels on its own through the wire. Same as if you dropped a little rock or pebble in the calm face of water. The pebble, let's say this is this is water, you drop a little little rock and it hits the surface of the water, and it's going to go through and it's going to land in the bottom here. So that rock is already not connected with that, but the waves each side, they continue, right? So it's the same idea. Yeah. Here's the idea of characteristic impedance, and some sources will tell you that it's the equivalent of 1 foot of the transmission line, or some sources will give you if the equivalent of 1 meter, depending on what you use for calculations. If you use meters, then you're going to use meters. If you use feet in calculations, you stick to the same unit in order to get the proper calculations on the other end. All right. So characteristic impedance tells us how hard or how easy it is for the amplifier to insert the wave into the cable so the wave can travel on its own. So if the cable is 100 feet long or is 1,000 feet long, the characteristic impedance does not change because it's just to match the impedances of the output impedance and the input of the cable. That's what the system cares about in this case here, right? Here is the formula for the Z0, which will be the characteristic impedance. The capacitance, the characteristic impedance is the square root of the inductance and the capacitance of the cable. Now, what do we mean by that? Well, in this case, it would be the capacitance per foot of the cable, because the cable can act as a capacitor. It has two conductors, and they are in close proximity to each other, and they have certain length, and they are separated by a dielectric. So, hey, you got a capacitor. And they also have inductance, because every physical thing that when you come to electronics or electricity, every physical thing will have certain resistance. It will have certain inductance. It will have certain capacitance. It just depends on how this, whatever the thing is, how it's built, which is the dominant quantity. And if we design a device and produce a device that its dominant quantity is capacitance and the other two are negligible, then we're going to call it capacitor. Right? Or same thing with the inductor, same thing with a resistor. So for now, we will not consider the pure resistive losses. Okay, so forget the pure resistive losses, because we also have to consider that because I square R losses. They also exist, but we're not going to consider them right now. So which is very little effect on the characteristic impedance. Okay, some common characteristic impedance values would be Cat5 or Cat6 cable, the Ethernet cable, which would be about 100 ohms of characteristic impedance. And let's say RG59 would be about 75 ohms. Where do I have those? Yeah. All right, so there'll be RG59, RG6, RG11. I didn't include RG58 here. So here's another formula for the characteristic impedance for the coaxial cable. And look, the characteristic impedance, whatever the number is here, then we're not going to get into it. And here is the K relative permittivity of insulation. So the type of dielectric plays a role. And there's that 138, whatever that comes from, we're not concerned about that, times the log of the diameter over the diameter, this diameter over this diameter. Nowhere here, my point is, and nowhere here the total length is considered of the cable. So point proven. Where do I have those cables here? Maybe it's not in this presentation. Do I have that? Yes, I do. Yeah. So here's RG59, RG6. The RG stands for radio guide. That's how those cables are. These are coaxial cables. That's how they are made. They were made for the purpose of the radar signals during the Second World War. So when the radar was invented, something had to connect the antenna to the rest of the equipment, and those coaxial or concentric cables, same thing, were invented. So those numbers, beside the RG radio guide, are just the cataloging numbers. And each cataloging number, because whenever some sort of specific type of a cable was developed, coaxial cable, it had to be categorized as something with whatever the specifications were needed at that time, or even now. Then the cataloging number will be 59, 6, 11, or so on. All right. So you notice that characteristic impedance of the RG59, RG6, and RG11, they're all 75 ohms. Okay. And then the RG58 is 50 ohms of the characteristic impedance. These are some of the most popular cables widely used. All right. Now, the amateur radio, the RG58 is quite popular for the amateur radio uses to connect the transmitter and the receiver to the antenna, and the antenna has to have the impedance of 50 ohms. The cable characteristic impedance has to be 50 ohms, and the output of the transmitter and the input of the receiver or transceiver has to be also 50 ohms. Then you have maximum power transfer all the way. If you mismatch those cables, then you're going to have some signal bouncing back into the transmitter if you are trying to transmit that. And here's another formula for the characteristic impedance. All right, simple calculations here. Commonly used coaxial cable RG8 AU. 8, I think, stands for the amended, which will be like enhanced, and /U. If you see the U thing, that means it's a UV rated, which means you can install that cable outside without worrying about that thing being affected by the sun, UV rays. Okay, so it has a capacitance per foot. See, it has a capacitance of 29.5 picofarads per foot. Okay, so that's so 1 foot of cable will have that type of capacitance. 2 feet of cable is going to have twice as much capacitance. Okay, so we have that. And inductance of 73.75 nanohenries per foot. All right, determine the characteristic impedance for a 1 foot section of that cable and for the length of 1 mile. Well, 1 foot section. Here we have the inductance and capacitance per foot. And the square root, you just apply those numbers. You're going to get the square root of 2500, and it's going to be 50 ohms. Now, the characteristic impedance is per foot. But if you want to consider the whole length of that, you can. It doesn't matter because you're going to get the same amount of feet. I have to multiply the capacitance, same amount of feet. You have to multiply the inductance, and you're going to divide that by that. Take a square root, you're going to get the same number. So, but usually when you have that per foot and per foot, Characteristic impedance in this case is the impedance of the first foot of that cable. This thing can be 10,000 miles, and the still characteristic impedance is going to be the same. Changing the wire diameter or spacing between the conductors can change the value of the characteristic impedance. A good cable design will have a inductance and capacitance value that do not change, uniformly made. Effects of the dielectric of the material. Any change in the dielectric material between these two wires or conductors can also change the characteristic impedance. So if you have different materials separating those wires, that might have an effect of the characteristic impedance. Typically, the dielectric material will increase the capacitance, resulting in a change of characteristic impedance. There are two formulas for the two-wire and for the coaxial cable. For the two-wire, the characteristic impedance is approximately equal to 276, here's a number, hard number, over the square root of the E times log of the diameters. Now, or the spacing between the two centers of those wires, and E is a dielectric constant or relative permittivity. And where do I have that? I think it's here. There we go. Permittivity, the resistance to the electric field. Farads per meter or per foot, depending on which ones you want to use. And the relative permittivity is a permittivity, which is resistance to electric field, which means basically how good insulator it is. Okay. It's the relative permittivity. Relative permittivity is permittivity of material with the reference of permittivity of vacuum. Okay. That's in short. So that's relative permittivity, and we have the E constant. It's the same thing when it comes to dielectric constant of the material. So here's for coaxial cable. Here's 138 square root of the E, and here's the diameter and the other diameter, which I just showed you the other formula, which is pretty much the same formula here. Transmission line losses. For many calculations with short transmission lines related to the impedance, we can assume that the transmission lines are loss-free if it's a short wire. How short? You're talking like few feet. Okay. From a practical standpoint, excuse me. Excuse me. Talking too much. There is a loss actually, because we don't, sometimes we don't transmit the signal over a couple feet. Sometimes we transmit the signal over 500 feet, 1,000 feet. Okay, so then we have to consider the copper losses because of the resistance. The energy will lose its power as it is traveling through a long chunk of metal. Okay. Dielectric losses, which increase with the voltage and the frequency. So even though the insulator is good insulator, but still some of the stuff gets through. And if you think about the wire as a capacitor, the higher frequency, because of the capacitive characteristic of the wire, the higher the frequency, the easier for that frequency it's going to be to jump from one conductor to another. It's going to get lost in the wire. So the high frequencies do not have as much travel distance in coaxial cables than the lower frequencies. The lower frequencies also have more meat on them. They have more oomph. They can travel through like a huge rock and it's going to take a lot. Once you swing out that rock and let it go, it's going to take a lot of power to stop that. So it will have enough kinetic energy in it. The small particles, like little small bearing balls or small rocks, they're going to travel a certain amount of distance, and they're going to stop quicker than the big rock. Yeah. So same thing with the high frequencies and the low frequencies. Um, and the radiation and induction. So if the signal radiates, usually on the connector, at the connector point, um, or induction, so it induces its energy onto something else, which means it loses energy. Where do I have that here? I keep coming back to those, that presentation here. Here's a table. You see here, let's say we're going to concentrate on the RG6 cable, which is the cable, the same cable that if you have internet over the cable provided to your house, it is that thickness. It's RG6 being used for the most part. Sometimes RG11, which is the same characteristics, but it has less losses. RG6 here, you see here, frequency 5 megahertz, and you're going to have, let's say, concentrate on per foot, and here's per meters. So the loss or the attenuation and specified temperature, of course. So 5 megahertz signal is you're going to have 0.69 decibel per 100 feet. Now, with that one there, 2.87, so it's almost like this is close to 3. So when you have a higher frequency, 211 megahertz, you see here, you're going to lose almost half each power over 100 feet. And look, you go, the frequency go, as we go down the table, the frequencies increase. And here is 3,500 megahertz as opposed to 500 megahertz only. It's going to have 12 dB or 13 dB almost, 12.85 dBs, decibels per 100 feet, considering that power, 3 decibels. Let me let somebody pick it up. Okay, I just don't want to talk over that. Okay. Okay, looks like somebody picked it up. All right, so that's beauty of the online teaching. All right, so you can see, considering that the 3 decibels is half of the power, then you can just tell how much of a signal is lost just per 100 feet. So this used to be a huge problem. Well, huge problem, not that huge of a problem because it could be remedied quite easily, but it was something that could not be just neglected. It had to be addressed. Like, for example, if there were cable TV channels being transmitted over the coaxial cable. So this would be some of the lower channels. This would be some of the higher channels. And if you have 200 feet or 300 feet of the coaxial cable going from the distribution amplifier somewhere in the basement to the classrooms, to each classroom of the school, some of the further classrooms will have clear channels on the lower channels, clear signal on the lower channels. And as you keep going up with the channels, then they would start looking kind of snowy or weak. How this thing was being remedied is by something that's called a tilt or a slope. Here's something that's called an RF amplifier, radio frequency amplifier. Of course, it's powered wherever the power plugs in. And here's the input, here's the output of the amplifier. Here's the gain, which is like the volume control of the radio frequency amplifier. Here's an input test tap out. So, because the signal from the city is coming quite strong, and if you want to plug in your TV set onto that one, it will not give you a proper signal. It might actually burn some circuitry in the TV. So here's a test point. It's whatever is here, it's lowered 20 decibels, so it's the signal will be acceptable by the regular input of a TV. And then over here, here's an output and also a test point at the output. So here's the mysterious tilt, or sometimes it's called slope. Okay, so if you have a signal coming from an amplifier, and you have, let's say, 500 feet distance of a coaxial cable. If you transmit the signals, so as you, let's say it's a high frequency signal, it's going to be strong in the middle and it's going to start lowering down so to the point that the low frequency signal is going to be quite weak at the other end. And the higher frequencies, so the lower frequencies, they will attenuate a little bit, but not as much. So it will be low frequencies, these will be the high frequencies. So the tilt or a slope is that at the amplification stage, the frequencies are transmitted with a certain type of a slope. So the lower frequencies are not amplified as much as the high frequencies. So at the beginning here, the high frequencies are high in power, and then they're going to come down here, and the low frequencies are going to meet sort of at the same level at the end. So that's why we have something that's called a tilt, or sometimes it's called a slope, depending on who makes it. So when you see that kind of stuff on the amplifier, on the radio frequency amplifier, or otherwise known as RF amplifier, that's what that is, okay? So from the calculations, short transmission lines rated impedance, we can assume that transmission lines are loss-free. From a practical, their losses do we need to consider? So copper losses, dielectric losses, radiation, and induction. Now here's a bit of a graph. What does this one show us here? We have a frequency in megahertz, so here's 200 megahertz, 400 megahertz, blah, 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 blah. And over here we have the attenuation, which is the signal degradation or signal becoming weak. So here signal is holding quite strong, and here signal is deteriorated a little bit. Here's deteriorated a little bit more. Here's deteriorated a lot. Okay, so and these are the different RG designations for different type of cables. RG58, well, the U thing here stands for UV rated, so that there's nothing that's nothing for us, but the RG58 and the specifications of that cable. So as the frequency goes up, looks like the RG58 cable has high losses as the frequency goes up. RG19 seems to be the best out of these. So you can get more signal through the more frequency. It looks like it has more bandwidth that can carry it through longer distance. All right, signal transmission speed. A transmission line can be imagined as a series of inductors and capacitors to the ground. So here's the coaxial cable or transmission, not necessarily coaxial cable. Any transmission line will have inductance, and the more you travel through that, more feet you go through, the more inductance is going to be accumulated. And once upon a time, you're going to have equivalent capacitance. These are imaginary, okay, but real. So here is the signal generator, and here is the characteristic impedance of whatever the load is. Depending on how long the cable is, you're going to have, well, the signal is traveling with the speed of light anyways, or the electricity, the electrical energy is traveling with the speed of light, not necessarily the electrons, but we're not going to get into it. So the electrons actually move pretty slow. The energy travels fast. So if you look at the signal, we're going to charge this capacitor, and then this capacitor, and that capacitor is going to keep losing time on charging all. So it's going to take time to propagate from one end to the other. So in order for a signal to propagate, there is a constant charging and discharging of voltages and the fields through the inductors that are going to delay the signal. It's going to take time for this. So the time delay is given by this formula. It's a square root of the inductance and capacitance, but that's for the characteristic impedance, so it'll be per foot. My laser. The velocity, which is a function of time and distance, here's the formula for that. How fast the velocity, how fast the signal is moving, based on how the delay is acting up on the. So a cable with more delay is going to take longer to transmit signal from one end to the other. The cable with less delay, the velocity of the signal is going to be greater. So here are the formulas here. Here's the velocity of the propagation. How quickly the signal propagates along the. Remember the characteristic that's called propagation delay in some of the integrated circuits or some of the parts? What is the propagation delay of an inverter? You might want to look it up. And that could be working against us, but of course, we can use it to our advantage. How? All right, something for you to think about. Okay? Now, let's go to the next slide. Speed of light and the delay lines. All right, let's see here. We can calculate the delay and velocity propagation in a cable if we know C and L, okay? So if you know C and L, you're good. You're laughing, right? Okay, what's C? C is the speed of light. And here's the inductance, the characteristic inductance. If we use the C per foot, and speed of light, and sorry, C. No. Take it back. I'm talking a bit too long here. My brain is getting tired playing tricks on me. Capacitance. All right? Here's the capacitance. Capacitance per foot and the inductance per foot. Okay. All right. So now if we know that, we can calculate things pretty quickly. All right. So here's an example. Determine the amount of delay and the velocity of propagation. Yeah. Introduced by a 1 foot section of RG8. Forget those designations. This amended and UV rated. We don't care. That's the specification. So of coaxial cable use the delay line. All right. So from the example, the other example that we used, we know the one that we have here, from this example here, RGA, we know that these are the characteristics of that. Here's the specifications. Okay. Excuse me. So from that previous example, we know that it has that RG8 has a capacitance of 29.5 picofarads per foot and inductance of 73.2. So we know that from that example. The delay introduced is quite simple, okay? The delay is per 1 foot. The signal is going to be delayed. Plug in those numbers, take a square root, apply the formula, blah, 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 blah. It is going to have 1.457 nanoseconds, which is pretty quick, but still, remember the Star Trek when Captain Picard says, have you considered betraying the humanity? All right, can't do that. So Captain Picard asks Data, have you considered betraying humanity? He goes, I did for about 1 nanosecond. And he says, but for Android, this is a whole eternity. So depending on what speed of the systems, what do we consider? This could be not much, or it could be a lot. Okay? So it was going to take, the signal is going to take 1.457 nanoseconds to travel 1 foot in that whatever. Okay, so RG8. And the velocity of the propagation, what's the speed of the signal? With that delay, so here's the delay. Here's the distance, 1 foot over that. So it's going to take 2.08 meters per second. That's going to be the speed of the signal through that cable. Apply those things here, okay? Resonant or non-resonant transmission lines. That's going to be the last concept we're going to tackle. As the signal propagates down the transmission line, two things happen. Well, we know that the signal is delayed. We know that the signal loses power on many different fronts. A non-resonant line is defined with a length of line that is terminated with the resistive load equal to the characteristic impedance of the line. So we want to have a non-resonant line because none of the signal is going to be reflecting and coming back at us, to us, hitting us over the head with if we have a maximum power transfer. The signal gets transferred from one end to the other through whatever connection, and it's just smooth transfer of the signal. It goes, nothing bounces back, nothing hits a brick wall. So that's a non-resonant line. We want to have a non-resonant line for the most part if you want a signal transfer. A resonant line is defined as a length of line that is terminated with an impedance that is not equal. So we have impedance mismatch, which is not equal to the characteristic impedance. And this could include a short or an open circuit. All right. Open or shorted transmission line represent extreme conditions where the maximum amount of energy is reflected back to the source, a result of impedance mismatch. Voltage on an open circuit wire is equal to the source voltage, and the current is 0 with open or shorted. Voltage reflection from the, okay, so for, you see here, I gotta change that. In the open circuit, the voltage is, and the current is 0. The voltage reflection from an open circuit is in phase, so a short, no, it's good. And for a short circuit, it's out of phase. Okay, we're good. I'm going to demonstrate that for you in a second here. The current reflection from an open circuit is out of phase from short in the circuit phase. Okay, so current reflection from an open circuit is out of phase. Here. Where did I find some kind of interesting website? Here. Right. Here we have something, some kind of a nice, cool simulation here. See, I can make waves with this. We have dampening a lot here, so I can just move that wrench and make a wave and send a wave down the line. Make a higher tension. All right. Or lower tension. Will be the impedance. All right, let's have no dampening at all. So I can just all right, let's do this thing here. Now we could have a loose end, which would represent an open in the line. We could have fixed end, which would represent a short. And over here, it would be just the impedances are matched, so the signal travels through. All right, let's see what happens if we have a signal shorted, if the cable is shorted on the other end. And did I make this thing with slow motion? Yeah. Look what happens. I'm going to manually move that wrench, create a wave. Here. All right. Wave travels. This is a shorted circuit. It's going to bounce back. Ooh, it's going to come out of phase. All right. It's going to hit the wrench. It's going to hit the source. It bounces back out of phase. All right. What happens if we have open circuit? Here's an open circuit. So remember, if it was a short, it comes back out of phase. Now, let's do it again. There's an open circuit. Ooh, it comes back in phase. This is not interesting. All right, just for kicks. If we have the impedances matched, it's just going to go through. Right? No signal losses. Right? Now let's see what happens if we start oscillating at the fixed end. And we're not going to do slow motion. Normal. Ooh, what happened here? Some of the waves are standing because they're going to get in phase. We got loose end here. Now we get even huger waves here. See that? And if we can adjust the length enough and the frequency, we are going to have some of those waves standing, amplifying each other. resonating. The wave, the energy adds to itself, and we have something that's called standing waves. Standing waves can be a huge problem. All right, stop that. Standing waves can be a huge problem when we have that kind of effect happening electrically. If you have a coaxial cable with enough power, you could have electrically voltage standing waves that are going to be here, and they're going to be bouncing up, bouncing off, and they're going to accumulate, and they're going to accumulate, and they're going to get bigger. And at some point where there's this point right here where the voltage is the max as its maximum, you can actually see some burn marks on the cable. Right here. The cable is basically becoming useless. So we want the line to be non-resonant. I want to see that. This represents a matched impedance. We oscillate, or hold on, send a pulse. The pulse just gets right through. If we have any kind of impedance mismatch, which would be fixed end, which would be the short, look, pulse is going to come back out of phase. Yeah. If we have open, it's going to come back in phase. Why does it change here? Because it's short comparing to the open, right? Here's the website. Pretty cool, eh? Now, just think about that. We know how things are going to behave, and we can determine the speed of the signal depending on the characteristics of the cable. Here is a device that is called time domain reflectometer. You input a bunch of data, what kind of cable that is, what kind of impedances. You have to kind of set it up, and you send a pulse through either coaxial, well, this would be a coaxial cable, for example, or any kind of line, copper. Time domain reflectometer. And depending on the speed, and because we have the characteristics of the cable, the specifications, we're going to see that, and that thing can have a lot of calculators going inside there. They're doing very fast calculations. And it's going to tell you that so many feet or so many meters from this source, there's a short. And so many meters, there's an open. Well, and it can tell you whether it's a total open or is it impedance mismatch. So when the line is broken, some of the technicians are going to apply that TDR, time domain reflectometer, and they're going to say, okay, looks like 700 meters from here, something huge has happened. So they go there, and of course there's a black hole that they hit the wire. Okay. Or if there is something that is underground, which is harder to detect visually, then this comes in really handy. So this is a time domain reflectometer, because we have a time domain. And based on that, we can calculate the distance. There's also a version of that for the optical fibers. So this one here for the copper, it's called TDR. And for the fiber optics, it's OTDR, which stands for optical time domain reflectometer. Right? And we're talking about standing waves. If things align, you could have standing waves, which is a problem sometimes when, well, in different situations. So electrically, I I showed you what can happen. The wires can actually get burned. Some of the sound waves can also have standing waves. Now, it could be a nuisance with some recording studios. We're trying to get rid of some of the standing waves that are going to add certain type of reflections or sound or distort some of the sound, especially for the bass guitar and all that stuff. So there are different dampening devices or physical things that can hang on the wall and wave traps that are going to dissipate the waves. So in sound and also with some of the church organs, there will be a big problem because you could actually make furniture vibrate with some of the lower frequencies. Some people say that you can actually break a wall or make the building kind of structurally be damaged. I haven't seen any of that happening, though technically it is possible. Some of the standing waves, what I had problem with when I was in that type of business a long time ago, is that some of the construction companies they wouldn't use the church rated chandeliers or light fixtures or whatever other fixtures that had to be church rated for the purpose of church organ. And there was one installation here in London. I'm not going to tell you where. They called me and say, "Hey, what's going on here? We can hear when we hit that certain key, something there's a buzz somewhere. So is there something wrong with the speakers or something?" I go, "Well, give me a ladder. Let me take a look." And on one of the back walls, and they have installed just a regular fluorescent light fixtures, because they didn't want to spend that much money, and they had to pay again to install the proper light fixtures because those were vibrating with certain. There would be a standing wave happening at that fixture because the length of the fixture would synchronize or resonate with a certain length of the wave, and it would start. It would have certain amount of standing waves, and it would start vibrating. Reflections. Okay. You know what? These few other slides, 1, 2, 3, 4, 5. Yeah. We're going to leave that for that hour that we're going to have in person. We're going to finish that up during that class, which is going to be on Friday. Cool. So this concludes today's lesson. I'm going to fix that and put it on our channel so you could watch that. If you want to try to fall asleep, you can read the electrical code, or sometimes you can listen to my voice. Although, if you go in short intervals, you might actually learn something and keep your attention span. All right, cool. Thank you so much for your attention, and I'll see you when I see you, which is going to be later on this week. Yeah, have a good day. Thank you. I always keep looking for those buttons here. Okay, stop recording. Thank you. Bye.